Okay, so first paper using topic modeling for code discovery in large-scale text data by Xinxiang Kai, Amanda Everstone, Brendan Egan, and David Williamson Schaffer. And I think, I hope that Xinxiang Kai is going to present it, right? Are you here? Can we see your image?
Yeah.
If you say something.
Yeah.
Welcome. Yes.
Thank you. This is Jiang Kai. I'm a researcher at medicine. Working
So
with
Xinjiang, let me just say one more thing because I forgot something important. We are going to do it like this, that we will have 3 presentations. Yours is the first, and they will be all around 10 minutes each. And after that, we will have a joint discussion of all the papers. So please remember your questions for all the 3 papers along the way. Sorry, Xinjiang, you go ahead.
Okay. I will continue. So this paper is about using topic modeling in discovering codes. So I have heard a lot about the different coding methods in this conference already. Basically, we have manual coding, all the way from manual coding to machine learning method like ROC. Is basically a manual coding tool that we had a wonderful workshop. And topic modeling is one of the machine learning method, which is fully automatically coding method, can be used as a coding method. And there are tools in between, like encoder or light side. These tools are sitting between. You just code part of the data, and then the machine can code the rest of it for you. So this paper is about how to, I know many people are using encoder, so we are trying to integrate the best practice from manual coding and automatic coding into encoder to say how all this can help us. So this paper is about using topic modeling, say how topic modeling can help encoder. We're trying to answer 2 questions. One is, can manual coding be replaced by machine learning? That completely, we don't do any manual coding. That would be super. Is it possible? That's one question. Second is, if that is not really possible, how does machine learning help coding? So these are the 2 questions we're trying to answer. So I guess here everybody knows the coding process. This is just a very high level summary of coding process. That's usually we need to create the codes by researcher, and then we code the data, and then after that we need to validate the code, the coding, whether or not we all agree on the codes or on the coding results. And so, for example, this is a real example of our previous study by Andrew and others. So in this data set, we coded 6 codes, real-world case, mesh repair, and others. The first column is the other codes. Second column, the definition of the codes. The third column are the rules actually we use to code the data. So we use encoder to define the regular expressions, and then we found the number of code words for each concept. Like a real world case, we had 8 code words. For mesh repair, we had 27, and so on. So these 4 codes will be used in this study. We use another data set, which is an engineering data set. We also coded this data and with 6 codes. And then these are the number of code words ended up with when we finish the coding using encoder. So just as for those who don't know encoder, encoder uses regular expressions to set up coding rules. So the number of code words is equivalent to the regular expression design finished in the encoder. So just so you have some idea, like for the medical data real world case, the code words are patient, patients, personal, personally. This is a group of words that are used to code the data and engineering. So this is just examples of code words, group of code words. So this is manual coding user encoder. Remember the code words that represents each code. And then topic modeling. This is a very simple way to understand topic modeling. So in topic modeling, we deal with documents, just like each line of textual data in our data set. And then we have a vocabulary. That's the list of words used in the whole data set. That could be large, thousands or tens of thousands of words. And then for each document, each word in each document, we assign a topic to it. For example, we have 10 topics. For each word, we assign a topic to it. From that, you can actually compute for each document what the proportion of words in each topic. That would be a topic distribution for each document. And similarly, you can compute in each topic what's the proportion of occurrence of each word. That's a word distribution in each document. You can compute that. Interestingly, from these probability distributions, you can come back to predict the topic assignment of each word, which may be different from the previously assigned. And then the simple mechanism in topic modeling is to repeatedly correct the assignment, recompute the probabilities, and until everything is consistent, then that's called topic model. So basically in the topic model for each topic, you have to assign the probability for every word. And then you sort the words with high probabilities. At the top, you'll find the topic words. And this is the result of topic modeling for the medical data set. Topic 1, at the top, you see ya, dong, that's from the don't. And the beat, move, these kind of things. Topic 2, topic 3, topic 4, each column is a topic. So the question we're asking is any of this topic, can any of this topic represent any of our code? So at the bottom, you see the 4 codes we designed. We want to say, obviously, they cannot really represent our code. But interestingly, like topic 4, the top one, mesh, is a code word we use in mesh repair, right? And topic 5, the second word, mesh, also is a code word we use in our coding. That's surprising because how does topic modeling know that we want to code this? Because we coded this without any communication with this machine learning mechanism. So this is still kind of surprising. So we are wondering how many code words appear in this top 15 words of the topic models. You guess how many will show up? That's a lot to us because the number of there are thousands of words in this data set. We only put up 15 words for each topic. That's 150 words. And then we have so this many topic words, code words appeared in the topic words. And each code actually has a representative in this top. So we did the same thing for the engineering data. This engineering data, we also did 10 topics. Now we have 6 codes. Now, if you just look very quickly, you may not see the code words. So these are the code words appeared in this. So from this, we see that none of the topic can really represent a code very well. For example, topic 2 in this data set, we do have 4 top topic words that are from performance. This is wonderful. However, you see other words are not. So they are just a garbage. So you see there's no clean representation of code. This is one. And also, if you see consultant, topic 1, top 1 word is consultant. And then topic 9, standards, is also from the same codes. So this basically spread it among the topics. They cannot just cleanly represent this. This is the bad side of topic modeling. The good side of topic modeling is, well, it does pick up the representatives of each code. If you see, we have 6 codes. Among the top 15 topic words, you see all the codes show up. So we find this is it's good. So when people argue that our topic model is useless, we cannot use it, but we feel like actually you can use it because the human coded code words show up here quickly.
Okay.
So how do we measure this?
You have to end in a few minutes.
Yeah, this is about end. So we created 2 measures. One is called the representativeness. That is to say how each topic can represent a code. Another is exposure ratio. That is basically the what the probability of code words in the top n topic words. This is a result. This shows that topic modeling are not very representative. They cannot represent the code very well. And this one shows that the blue ones are the code word exposure rate in the topic modeling. And the orange one are in the random words. You see that there's a much higher code word exposure rate in topic modeling. And this is the ratio. So the topic modeling is about sometimes about 10 times more exposure rate than the random words. So this tells us that topic modeling helps us to discover the codes and help us to complete code rules. And it can also be used with other techniques like word frequency, LSA, and other techniques. The take-home message is machine learning may not replace human coding. However, machine learning helps discovering codes. Yeah.
So thank you very much, Xingyang. We will wait with the questions until after the session. So we will go right at the next. Well, we should. Thank you. Great. This is weird, but I do like this, right? Thank you. The next paper, we go right at it. It is Ha Nguyen who will talk. I think it's you that are presenting, right? Ha?
Yes.
And you will talk.
Unless there's another Ha and group.
Yes, you're there. Thank you. And establishing trustworthiness through algorithmic approaches to qualitative research. And please go ahead.
Thank you. Ha, I'm a graduate student at UCI and I'm representing a group of researchers, educator partners, and nonprofit organizations from Orange County Education Advancement Network. So a little bit of context about this work. Large March schools in the US shut down because of COVID-19 and everybody just moved to distance learning. And our partner educators communicate this need for us to quickly understand the landscape and experiences of everyone, so as they can respond quickly in the fall. So in May and June of 2020, we conducted in-depth interviews with 35 stakeholders, so district administrators, school staff, and educators in the US. And we have a need to conduct these rapid analysis of this very large interview corpus with a quick turnaround for a partner before the school year start. So we thought about the feasibility of introducing algorithmic approaches into our analysis. And this shed light throughout the process as we try to combine the insights from the algorithmic coding and the human researchers' insights. So this is more like a self-study that walked through the process that we went through. And then for each step of the way, we discuss how to introduce more rigor in this process. So a little bit of background, what do we mean when we talk about trustworthiness or rigor in qualitative research? Lincoln and Guba propose these different criteria for thinking about trustworthiness. So you want to see whether your data is believable or not, whether your analysis is dependable, and whether the analysis trail is also confirmable by other researchers. So to set these different criteria, there are multiple strategies that you can use. So normally in qual research, you can think about triangulating your different data sources. You can do member checking, you can do inter-rater reliability, and you have to clearly communicate your data analysis trails of how the data was collected and analyzed for other analysts and researchers to try to trace back to this data. So how do we bring the algorithm into this process? I think the previous presenter also hinted this process where basically you have two ways to look at the data. One, you can already have these predefined themes and you go in and you can use backup words, word counts to look at, or topic models to look at, word counts to look at how these words map onto the categories. And then on the other end, you can do some bottom-up analysis where you look at the word clusters, you can look at topic models to see which types of topics emerge from this analysis. And each of those has different challenge. One involves very intensive research labor upfront, while the others also need to bring in the human insight to make sense of the patterns that is uncovered through the computation. So what we did with analyzing our data corpus is we use these two approaches, the inductive and the deductive approach, and we try to look at the data. So for the deductive approach, we already have some themes that we had in mind when we built out the interview questions. For example, relating to food security or distance learning strategies or teacher collaboration. And basically, we try to identify the words that are semantically similar to these keywords under each themes. For the inductive approach, basically we just do a word clustering using word embeddings for the text and then try to calculate the distance between the text. And I don't want to go too much in depth into the algorithms because those are described in more details in the papers. But here I just want to illustrate the output from the two approach. And what you can see here is that they turn a very different output. So for example, if you look at the distant learning clusters from the bottom-up analysis, you see words like mastery learning, emergency learning. So it hints more at like types of learning clustered together. Whereas if you look at the same topic clusters from the pre-identified keyword analysis, you see different keywords, right? You see face-to-face, you see model, brick and mortar, mental health. So more getting at the how responses of the distance learning. So we want to see how, if we bring these output to researchers who are not familiar with the algorithms, how they react to that. And what we did is we invite the rest of our research team, where I'm the facilitator, and then half of the group are looking at this word output, and the other half are looking at the inductive output, and we try to make sense of it. So an insight that emerged from this sharing section is that any given output will substantially influence the analysis direction of the research team. And this has implications for how you want to establish credibility and confirmability in your results. So this is a quote from a fellow researcher who say that how she makes sense of the output really depends on her added knowledge and experience of the human insight. And as I hinted earlier, when you look at the vocabulary from these different word clusters, you immediately think about very different types of questions that you can ask, which will influence the subsequent analysis. So a researcher looking at the distance learning cluster may ask questions such as, how are schools and districts implementing distance learning? Whereas a researcher looking at the word cluster from the topic model about like distance learning, mastery learning, or emergency learning may ask questions such as, what types of learning responses are being offered? And our insight here is that we want to clearly communicate these analysis steps between the algorithms and the human researchers. And so here we have a very basic roadmap of how we define the code mappings for the distance learning code, going from the themes to the keywords, to the algorithms, to the output, and then to the human insights. And what we want to communicate here is that by mapping these conjectures very clearly, you can work towards establishing whether your data output is credible or not, and whether other analysts can look at the data and confirm your analysis. We also experiment with using encoder to establish iterative reliability. So here we treat encoder as another researcher in the process to try to calibrate the code with. And we observe quite a range of variance in the iterative reliability, mostly because our training set is very small. And so this also has implications for how you want to communicate this and how you want to improve the training process to establish dependability when you involve the algorithms. And finally, we aim to establish a form of triangulation using insights from the algorithmic approach by using visual analytics techniques such as the epistemic network analysis. So here we have examples of an ENA built on the two approaches, one from the inductive, so the word clustering, and the other from the deductive, so the predefined topics. And you can see that like the two visualizations communicate different patterns that may also trigger further questions in analysis. So for example, here, we look at three codes, right? The teaching and learning, the distance learning, and the district intervention themes. And you see that principals are focusing more on the teaching and learning and distance learning part, whereas district administrator, which is the green one, is talking more about teaching, learning, and district intervention. And so when we present this to our fellow researchers, they have questions such as like, how do these different roles respond to the distance learning challenges, and what are their like main concerns and concentrations, leading to more fine-grained analysis of the qualitative corpus for these specific roles. And or takeaway here is that algorithmic and ENA approaches could be seen as another form of triangulation. So looking at data from different viewpoints to strengthen the overall analysis and also open up opportunities. So in closing, we go back to our original question of how can we establish trustworthiness in qualitative research when adopting human-computer analytic approaches. And we go back to these dimensions of trustworthiness: credibility, dependability, conformability. So in our study, we used different algorithms. We used an automated classifier to establish iterative reliability. We used code mapping to lay out how we combine human and algorithmic interpretation. And we also use a form of visual analytics for triangulation as a form of constant comparisons. And this is by no means extensive, but we hope to open up the conversations for the community towards thinking about what type of system of data exploration, analysis, and triangulation we can build for the analysts and researchers doing this type of work.
Thank you very much. And yes, and great presentation. We move right on, right, and to the next paper, which is called How We Code. So now we learn how to do it. Andrew, you're going to present, right? Or is it?
Yeah, I am.
Okay, so Andrew Ruiz and How We Code, and you can present yourself and where you're from and so on. 10 minutes.
All right, thank you, Martin. Hi, everyone. I'm Andrew Ruiz. I'm at the University of Wisconsin-Madison, and my colleague David Schaefer and I really put this together as a way of starting to create a common understanding of coding in QE. And so this is a little bit more of a summative paper than any particular new direction, but I think as the two previous papers demonstrate, there's a lot of really cool stuff happening in coding and starting to get a kind of shared language around how we think about coding might be very useful. So coding in a QE context is really, as everybody here I think is fairly familiar with, an issue of how we move from the sort of events in the world that we care about to interpretations of those events. And one of the kind of key linkages between those things is the linkage between big C code and little c codes. And when we talk about coding, one of the things that's really critical that we talk about is actually fairness. And fairness, it really is taken in three respects in this case. So there's fairness to theory, fairness to the community or the culture from whom we're interested in, and then fairness to the data itself. And we present evidence of this fairness in a few different ways. So one of the main ways is through a code book, where we give the name of a code, a definition of the code, and examples. Now, it's typically better if we give a more robust definition and if we give multiple examples to really give a clear sense of what we're talking about, because this is a key way in which, for example, the definition helps us connect the big C code to theory. And really the whole set of entries is our evidence of fairness to community, that these things are meaningful in some context. And the examples themselves are drawn from actual data so that it's very clear how we would see these codes out there in the world. So we can take any given example. This one happens to be from Game of Thrones. You can tell that David is the one who built the examples. One person, researcher, could go through and, in the case of the code of violence, could go through and actually say, look, this is an example where we don't see any indication of violence in the line. In the next case, though, there's a talk of beheading, so we do see an indication of violence, and so on and so forth, going through and basically hand coding and showing that this concept of violence shows up in some places and not in others. So it gives us some evidence of fairness to data. And of course, that's only giving us one person's perspective. So we have no real way of knowing how certain we can be of that perspective. So of course, typically we would have another rater also do the same thing, although typically only on a subset of the data. And we can see that there will be cases in which the two raters agree and cases in which the two raters don't. In this case, because the second rater noted that ambush is evidence of the code violence that the first rater missed. And to get a sense of the extent to which these two raters agree, we typically compute some measure of inter-rater reliability. In this case, we're talking about kappa. It's one that's very commonly used, although there are plenty of others that are used in the field. And the reason that we do that is that we are trying to get some measure of how uncertain the coding is. So when we only have one rater, we have no bounds on the level of uncertainty there is. But when we have two raters, we can put a limit on the extent to which there's uncertainty in the coding itself. And the smaller that area of uncertainty, the better the agreement. When we have good agreement, we have less uncertainty about the coding. And as we add additional raters, that area of uncertainty gets smaller and smaller, although we have to do it in a way that does pairwise comparisons amongst all raters, because if we, for example, only compare two of them, then it actually makes it even worse. We get even less bounding. So one of the things that we have a problem with, though, is the fact that we've only measured our agreement for some subset of the data. We don't know what the agreement would have been for the entire data. And so, for example, if we took a set of 80 excerpts and we compared the ratings of 2 individuals, we might get a kappa of 0.91, say. But we don't really know if that kappa should apply to all of the data, or if it really is only a measure of what's going on in those 80 excerpts. And so in other words, we aren't controlling for type 1 error. We don't know if we applied that kappa value to the whole set, if we would be doing so erroneously. So this is where rho comes in, and rho is a very useful statistic because it allows us to compute a probability that if those 2 raters had coded all of the data, that they would have they would have achieved a kappa of at least whatever the threshold is. In this case, a threshold of 0.9. And one thing we note is that it's actually fairly common for people to use relatively low thresholds for kappa. And I have been as guilty of this as anybody, but often, 0.65 is a common one that's used. And we argue, and can't get into too much in this presentation or this paper, but we argue that that's actually a very low threshold. And so we're sort of pushing for higher thresholds. But of course, the volumes of data that we work with, we often also need to use some kind of machine coding. And so the 2 previous papers discussed, it's actually really important that we figure out how to work a automated process into the loop. As we suggested earlier, the machine may not agree perfectly with the humans either. And so one of the ways that we handle that is we compute kappa and rho between each unique pair of raters, called a triangular validation. And of course, in a paper, we have to report this, across all of the different ratings, and that all of those pairwise agreements have to be above our threshold. Our rho has to be acceptable in all cases. And the reason for that is this is the other way that we provide evidence for fairness. Now, of course, as the previous presentations have made clear, a lot of times it's useful to use things like topic modeling, other natural language processing approaches to help you generate codes or to help you refine term lists and things like that. Of course, as in Carl's presentation, he pointed out, this involves a training set, right? So you need to take out some subset of the data to do this one. And you also are going to generate some spurious terms, right? You're going to get topics that aren't perfectly aligned with a big C code. And so one of the things that has to happen is that a human has to come in and actually prune those lists, or actually see what the models produce and integrate that perspective in. And so in this case, pruning out words that are not very useful. And then, of course, as we mentioned, there's this 3-way validation. And the problem with only validating with the computer is that it only gives us evidence of fairness to data. To get evidence of fairness to theory and to community, we actually need to compute between 2 human raters. And so that's the kind of core of this idea of triangular validation. And it's also really important that we use a holdout set when we do that kind of validation, because you don't want information leakage to happen when basically the same excerpts are used to train a model as to test that model. And we can talk about that in a little bit more detail if people are interested. But basically what we need to do is split out the data in some principled way, which may or may not be randomly assigning excerpts to different buckets, But we need to make sure that the data that we use to train our coding system are not a part of the data that we use to test that coding system to validate it. So this is a very, very brief overview. The paper itself goes into a lot more on the principles and practices for code generation, transcription and segmentation, how to manage training, holdout, and test sets. There's a lot more about inter-rater reliability testing. We talk a little bit about contextual coding or derived coding. But all of this, I think we need to have this discussion in the context of fair coding. And I think that's a key piece that we haven't really been talking about enough in the QE community. But with that, I will end the presentation, and hopefully we can have a discussion about these and other coding issues.
All right, so thank you, Andrew. So super. So I think we are going to do it like this: that if you have a question, you put an X or something like that in the chat, and I'll try to moderate. Maybe you actually ask. Maybe you actually write who you have a question for. Let's do it like that. So and so I will keep an eye on the chat, and while you are thinking about whether you have a question or not, I'll ask a question myself. Okay, this is, I think, for you, Ha. I mean, what the way we talk about the use of, actually it's for the first two presentations, the way we talk about topic model based coding and related to what human coding would be, I would think, aren't we just seeing our own pre-assumptions when, I mean, aren't the NLP codes better in a sense, because they are making a more, we don't get our own pre-assumptions for the categories. So what is your reflection on that? I mean, so you have the deductive coding where you have your pre-decided codes, and then you have the topic modeling that gives like a more only look at the text. There are some advantages in the topic modeling, I think.
Yeah. So for our work, so many people just use topic modeling and use the topic as codes, right? And of course, we understand that that can never match human coders' intuitions or theory, right? Sometimes we code by theory. We say, hey, I just want to look if this code or this code is in the data, and I don't care how much it is in the data or whether or not it is in the data, but we just, from theory, we just want to code it. A topic model basically just code the most frequent concepts that is used and semantically related in it. So we know that cannot match our intuition. The question is how we can use it to help us. When human code it, sometimes we don't know what to code. Without theory, especially the data grounded coding, we just want to discover what is in the data. But topic modeling can discover that for us. At least it can discover the most frequent topics for us. I think in that sense, topic modeling can be combined with human coding in the sense that it can, one, help us to discover codes that we didn't think of, especially for something that is deeply hidden in the large-scale data that could be useful. Another thing is, even if we know the codes, but we may miss some, like in encoder we use regular expressions, we may miss some code words. Topic modeling may help us to make this complete. So this is just, yeah.
Yeah, thank you. So, but for instance, how I was thinking about when it was like your topic modeling codes or inductive codes painted an entirely different picture of what online learning was, right? Um,
Right. So I think it just goes back to like the purpose of using these things. If you're only like trying to explore the data on a very broad scale, then you can use the inductive approach. But what we found out is like it turns out very wildly different words that it's quite hard to make sense of it, and you can go in very different directions as analysts looking at them. Versus when you use the deductive approach, you like if you have the predefined words and categories, you may have still some grounding and theories going in. So for that, you may have a more focused analysis aspect.
yes, but my question was actually maybe you are coding for your own like pre-assumptions.
Mm.
So the topic modeling saw some good things in distance learning that was actually not in the, as far as I remember, right?
That's true. That's true.
Okay. Okay. So any questions? Anyone that is going to help me, or should I? Um, maybe I just wait.
So
Jamie?
I mean, so I have yeah. My question was kind of very similar to what you had, Morten, around inductive versus deductive and how you go about deciding and how deductive can what's the right word, introduce or introduce like interpretation creep, I guess you could call it, in how you look at those that data and make your conclusions. And I mean, I just from my own understanding and my limited knowledge around classic discourse analysis, inductive coding has several more advantages to deductive. Is that correct? Maybe somebody wants to correct me on that.
I think this is. I mean, you can find both views. I would say. I mean, this is just if you're red or blue, right? But I mean, you can definitely find proponents for an open coding approach. So,
Well, can I respond?
anyone wants to add to this? Andrew?
Yeah, I can just say something real quick to your point, Jamie. I mean, there's this sort of one of those classic, like, it depends kind of, moments. I mean, I think there are a lot of people, right, who are really interested in characterizing what's in a data set, right, some body of texts or whatever it is. And to Martin's point, right, they don't want to come in with, okay, here's what I'm looking for, and I want to go find it in there. Yeah, they want to know kind of like sort of what are the things that shake out of this in whatever sense of know that is. So that's sort of your classic kind of text mining, NLP, other kinds of things. There are perfectly good reasons you might want that sort of approach, and there are equally good reasons that you might want to go into a data set completely from that kind of grounded qualitative perspective. Like, nope, I understand this community or this culture or this context, whatever it is. These are the things that I know are salient, and I need to find ways to identify them in this data. And this is getting to, back to Carl's point about like, what you need to identify, and these sort of more agnostic tools can be useful in just making sure that you've thought of all the different terms and other things that you might want to include in order to do that. And there's sort of a bunch of things in between. And I think it really depends on what it is you're trying to do. I think for most QE contexts, we're more in that camp, right? We're more in that tradition of understanding the context and having hypotheses or theories about what's going on, and wanting to kind of find ways to examine them at a scale where we can't just sit down and read everything or sit down and view everything, depending on kind of data. And so I think that's much more common in QE, but I mean, maybe even within QE, but certainly without QE, there's plenty of context in which you might actually care about, these kind of larger scale statistics, even absent any particular hypotheses about what's going on. But I think it's also that we need to understand them better. I think like both Carl and Ha's studies are really important because it's helping us to figure out like what is the difference between these approaches and what are the affordances and trade-offs of picking different ones. And I think that's still very wide open, certainly wide open in QE, but even in discourse analysis more generally, I think there's a lot of work that still needs to be done on that front.
Okay, thank you. If no more comments to this.
Yeah, I do have, sorry. So
No,
I do have a comment, and I actually think instead of the dichotomy between the deductive and inductive, can't we have like a kind of integrated coding where you have what you're actually hoping to see in the data? That means the deductive based on theory or whatever. Then in grounding it again, you're also looking at what the data kind of tells you. So I think it's fine to kind of have what you're hoping to see and having those deductive like approach to it, and also like taking the inductive approach to it. So you could like kind of meet in the middle, because I try to consider when dealing with things like tweets and probably other data where you really don't get to like interview people, but you scrape this kind of data, and sometimes people could really be bringing up so many words, but then they could be sarcastic in a way, or they could actually be giving it some other meanings that kind of takes the human interpretation to know that, okay, these, even though this word is appearing like this, it has another meaning in this context. I think that's one way where the deductive approach could kind of compensate for the inductive, because inductive basically look at what word is reappearing, how often does it comes up, but then you can't deny the fact that it kind of leaves out some context in a way, especially when dealing with dynamic, like human nature like that. So I kind of say the two. I don't know whether that's just me, but then I kind of see the two as very useful and using them together in a way, especially when dealing with big data and big discourses like that.
Thank you, Yoba. So is there any specific question to one of the three presenters, or is there any one of you that presenters that wanna say something here? I mean, you're obviously completely right that we need to balance and find a good interplay between these approaches. Okay, then I will go on to the next question, which is from Sue, which is a clear statement in the chat. I mean, basically, I mean, maybe you want to say something yourself, Sue, but you're saying that you cannot only do machine learning, right?
Yeah, I think for part of what I'm wondering about is if the meaning units within your data are embedded in a narrative format. It seems to me that if the narrative is carrying a lot of the meaning weight, then NLP is going to miss stuff. I mean, and anything we do misses stuff, right? I mean, that's a given. But I think it really, in addition to what your question is, I think it also must depend some on what the data are like. Not just the size, you know, is it, I mean, I think the first pass a lot of us would make is, do I feel like I can hand code this? Yes or no. But I think also the type piece, and some of this is, I've been working with indigenous communities where storytelling is a really central way of communicating information. And to cut a story up into little pieces is sort of to do violence to that way of understanding and that way of communicating. So I guess I'm getting a little more philosophical about this than maybe is helpful, but it's useful to think about which tools are best for what uses.
If I could just,
No.
Oh, go ahead, Andrew.
Yeah, I'll just respond to that really quickly, which is that I think even from like kind of classical ethnographic perspective, right? I think there's also new challenges because the kind of way that we get to know a community, a culture, that sort of thing, it might be very difficult in some modern contexts. I mean, think about social media, for example, is so massive that you could spend your whole life on a social media platform and still not have that full sense of, a sense of it, or want to study some aspect of it that you can't really experience in some way. And I think so. I think there are for even like kind of traditional classical ethnographers, this is a big challenge in many ways. And the people that want to do sort of digital ethnography, I think there's obviously a lot of good work on it already, but also I think it does raise these kinds of questions, and obviously there are other contexts in which that comes up, but I think that's just a very easy example where you have the combination of there's massive amounts of data, right? So that even if you did want to read a bunch of it, you'd barely be able to scratch the surface. And this sense of like, could you even really wrap your arms around it in any kind of traditional qualitative sense? And I think that's a case where thinking about the interplay of these approaches is critical. And it's something that we've thought a lot about with Encoder and really trying to maximize your ability to qualitatively engage with something while sort of minimizing the amount of work you would have to do to actually validate something, right? And I think that's a kind of that's sort of one way in which this matters. And to Carl's point, right, that code generation is a real challenge, especially in big data sets, even when you really know the material well, and that there are techniques you can use that could make that process faster, easier, and more effective. But we have to figure out how to integrate them into our workflow for these sorts of things. And the same thing with the kind of stuff that Hal is showing, where you might see the same thing from very different perspectives, and now it brings up this question of like, well, should we incorporate both of those? Should they all come into one code? Should we have separate codes that kind of capture those different pieces? I mean, there's, I think, a lot of really kind of interesting fundamental questions that arise from, from this kind of work. And that's why I was sort of saying, I think there's a lot of really cool things that are going to emerge from figuring out how sort of human interpretation and kind of machine pattern finding can be merged in various ways productively to improve the kinds of analyses that we do, even when we're really grounded in that ethnographic perspective.
I think that's right. I really agree with Sue that machine learning cannot do it alone because it cannot read a researcher's mind remotely without so kind of interactive machine learning coding could probably be the way to go. Imagine there's a machine in front of you. You don't need to do any coding. Just talk to the machine to say, actually, I want to say if this is in the code, is in the data, can you try that for me? The machine, I will do that for you. It's conversational. And the machine is so smart in the future, not today, but the machine will be smart enough. You just easily talk to the machine will eventually find all the code for you. I think that's because machine learning is making huge progress recently. So I think that is possible in the near future that will happen.
Yeah, I was just going to add that a lot of Judea Pearl's work really emphasizes the discrepancies with machine learning and AI. Is anyone familiar with Judea Pearl? So Judea Pearl is sort of a causal guru, and he has worked on machine learning since the early 80s. And he argues that in order for machines to truly mimic that of human intelligence, they have to have the ability to reason by association with causal reasoning, instead of just the ability to correlate what one thing with another. They need to have that capacity for what causes something else. And that framework we just haven't been able to to replicate that in a way that mimics the human way of thinking. And he writes a really great book. I'm not sure I recommend everybody check it out. It's called The Book of Why. But he really goes on to say, it's about that Bayesian way of thinking where we have the ability to look at information and based on past experiences come up with different reasonings, but also consider the counterfactual that exists, and machine learning just is not there yet. It's a really interesting read. I recommend it.
Yeah, it may never be there, but I think the interaction is the key. So machine does machines work, human does humans work, right? You can do reasoning, okay, you reason. The machine can do computation for you so that can quickly do some simple reasoning for you, and you reason yourself, machine learning just make it quicker, faster. I think that's a
So we're slowly reaching towards the end of this session. I will just say something briefly, which is, I mean, several of you mentioned triangulation, and I think this is an important part of also what Sue says here. I mean, of course, the idea is not to just lie on the sofa and let a machine do the ethnographical work. That makes no sense, right? But maybe we can see something. Maybe we consider the first topics that the topic model suggests and say, okay, what does this mean? Maybe that's always a good idea. I mean, it is something like that. Okay, so we need to end. I don't know if you can continue in some other cyberspace coffee break or whatever, but thank you for wonderful presentations and interesting discussion, and see you later, right?